Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Professor Morales. Thanks for meeting with me during office hours to talk about grid storage solutions.
Good afternoon, David. Tell me about the specific angle of grid storage you want to focus on for your thesis.
I want to analyze battery technology for renewable energy integration. I am comparing lithium-ion systems and flow batteries for utility-scale applications.
That is a timely topic. When we say grid storage solutions, we need to clarify technical metrics like power rating, energy capacity, duration, and round-trip efficiency.
Could you explain how those metrics influence which technology is appropriate for a given project?
Yes. Power rating measured in megawatts determines how much load the system can handle instantaneously. Energy capacity measured in megawatt hours tells you how long it can sustain that power. Duration is capacity divided by power. Round-trip efficiency measures energy lost during charge and discharge.
So a 50 megawatt system with 200 megawatt hours has a 4-hour duration. That seems standard for peak shaving.
Exactly. 4-hour systems are common for capacity shifting. For frequency regulation, you need high power for short durations, sometimes seconds to minutes. For seasonal shifting, you need much longer duration solutions.
You mentioned round-trip efficiency. How efficient are lithium-ion systems compared with flow batteries?
The round-trip efficiency for lithium-ion systems is around 85 to 95% depending on conditions.
That is quite high. Does that mean lithium-ion always makes sense economically?
Not always. You must also consider cycle life, capital cost per kilowatt-hour, degradation over time, and thermal management needs. Lithium-ion offers high energy density and efficiency but has degradation from deep discharges and elevated temperatures.
How do flow batteries compare on cycle life and duration?
Flow batteries like vanadium redox tend to have long cycle life and can be designed for many thousands of cycles with minimal capacity fade. They have lower energy density but are scalable for long-duration storage by increasing electrolyte volume.
So flow batteries are better for multi-hour or daily shifting, while lithium-ion is better for short-duration services and locations where space is limited.
That is a good generalization. Also consider round-trip efficiency differences. Flow batteries often have lower efficiency, maybe 65 to 80%, but the long cycle life and stable chemistry can make them cost-effective for long discharge durations.
Can you give an example of a real-world deployment that illustrates these trade-offs?
Yes. The Hornsdale Power Reserve in South Australia is a lithium-ion system that focuses on frequency regulation and fast response. It demonstrated how a high-power, short-duration battery can stabilize grid frequency and reduce ancillary service costs.
I read about that case. Are there similar examples for long-duration battery storage?
There are demonstration projects using vanadium redox and other flow chemistries for 4 to 8 hour applications. Utility pilots in California and Europe are testing economics of multi-hour systems to shift solar generation into evening demand.
How do control systems and integration differ between these technologies?
Integration requires a battery management system, power conversion system with inverters, and grid interface controls. Lithium-ion BMS focuses heavily on cell balancing and thermal runaway prevention. Flow battery systems emphasize pump controls and electrolyte management.
What about DC coupling with solar farms versus AC coupling for these storage systems?
DC coupling can be more efficient when connecting storage directly to a solar DC bus because you avoid an extra inversion step. AC coupling offers more flexibility with existing inverters but may incur slightly more losses. The choice depends on project specifics.
You mentioned safety concerns. Should I include thermal runaway risk and fire mitigation in my analysis?
Absolutely. Lithium-ion systems require strict thermal management, fire suppression planning, and site spacing rules. Flow batteries have different failure modes and can be safer at cell level, but they require handling of chemicals and containment strategies.
How should I compare costs between technologies in the thesis?
Use levelized cost of storage metrics like cost per megawatt hour delivered, accounting for efficiency, cycle life, replacement costs, and round-trip losses. Also run scenario analyses for different services like frequency regulation versus energy shifting.
Do you recommend including policy and market revenue streams in the model?
Yes. Revenue streams from capacity markets, arbitrage, demand charge reduction, and ancillary services significantly affect economics. For example, batteries that provide frequency response can be paid per event, which can change payback calculations.
Are there emerging chemistries I should mention to show future trends?
Include sodium-ion, solid-state, and metal-air developments. But be clear about their current technology readiness levels. Many are promising, but not yet proven at grid scale.
For my case studies, I plan to model a 50-megawatt lithium-ion system for peak shaving and a 20-megawatt vanadium flow system for long-duration shifting. Does that sound reasonable?
Yes. Make sure you specify energy capacities so you can compute durations. Also include round-trip efficiencies, degradation assumptions, and maintenance costs for each case.
I will. Any recommended data sources for cost and performance metrics?
Use manufacturer datasheets, recent utility procurement reports, and academic reviews. Government energy labs often publish neutral datasets as well.
Great. I will draft a modeling plan and bring it to our next meeting. Thank you for the guidance.
You are welcome. Send your draft and include the assumptions on efficiency and cycle life, so we can test sensitivity to those variables.
I will. See you next week.
See you then.
Listen again to part of the conversation, then answer the question.
The round-trip efficiency for lithium-ion systems is around 85 to 95% depending on conditions.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.